Alright guys, this is notes on section 2.4, part 3, the remainder theorem. This is an important theorem, but it's one that we don't really consciously use it. It's going to be really important for 2.5, next section, but it's something that we don't just sit there and think about and use all the time. So what it's basically wanting us to do here is, if we take any polynomial and divide it by x minus c, think about how in synthetic division that would mean c is the number that goes in the box. And the remainder is f of c. The remainder would be what you would get if you plug that number that goes in the box in synthetic division into the function itself. It's going to be your remainder, which is interesting, but it's really important for the next theorem that we're going to see, the factor theorem. But anyway, let's just show first of all f of 2 means plug 2 into this. So that's 2 cubed minus 4 times 2 squared plus 5 times 2. Right? That's just what f of 2 means. So 8 minus 16 plus 10 plus 3. Alright. That's 18 minus 16 is 2 plus 3 is 5. So what this is saying, the remainder theorem is saying, is we should expect a remainder of 5 when we do this long division here. Okay? So f of 2, right, f of c, c is what we're dividing by, so that means 2 is what we're going to use in the synthetic division. Alright, my coefficients are 1, negative 4, 5, and 3. Alright, bring down my 1. 2 times 1 is 2. Add these, I get a negative 2. 2 times negative 2 is negative 4. Add these, I get a 1. And then 2 times 1 is 2. Add these, this is my remainder. And I get a 5. Which is the same thing I got when I plugged 2 into the function. Alright, so very interesting theorem, but that's all it's saying is whatever you get when you divide by x minus c, meaning long division using c in the box, is the same thing you would get if you just plugged in c into the function. Right? Very interesting theorem. Okay, but where is it useful? Why do we need to know it? Again, it's not going to be one that we use on its face, but this is why it's important. The factor theorem is basically an extension of the remainder theorem, and it basically says if you plug c into a function, a polynomial, you get 0, which means it's a 0 of the polynomial. So if c is a 0 of the polynomial, then x minus c is a factor of f of x. Well, that comes directly off of the remainder theorem. Alright, the remainder is f of c. The remainder is 0. If you divide by this, x minus c, you get a remainder of 0. That means this thing's a factor. It divides the original function evenly. When you do long division or synthetic division, you get a remainder of 0, then that thing right there is a factor. Alright, and then it's if and only if, so it works the other way as well. If that's a factor, if a line basically divides a polynomial, then when you plug in that thing that makes this line equal to 0, it's going to make the polynomial equal to 0. Alright, so this is what we're really going to use. We're going to use this in 2.5 a lot. Okay, but again, it's just basically a check. You know, it kind of gets us, down further along. So what we're going to know is when we plug something in, we get 0. That means that that thing is a factor. But it's just like x squared minus 9 is x plus 3, x minus 3, right? The thing that's important with the factor theorem is when I get a factor, I know something's going to be a factor because when I plug in a number, I get 0. So this thing is a factor. The thing about the factor theorem, though, is if I divide this polynomial by this factor that I now know because I plug in and get 0. Then when I divide and get a remainder, remember when you divide you get a quotient, you get another factor. That's the important thing here, is we're going to be able to factor these polynomials that we've never been able to factor before based on the zeros of the polynomial. What plugs in gives me a 0. Alright, so let me show you what we're talking about here. I'm trying to come up with the solution to this. This is a cubic. Now we got 1, 2, 3, 4 terms. So in the last section, I would say, all right, let's factor this by grouping because we've got 4 terms. So I group the first two together, I group the second group together, separate them with a plus. The GCF here is x squared. 2x, that leaves me with 2x minus 3. The GCF here, there isn't really one, but I said, remember, if there isn't one, and it leads off with a negative, then pull out a negative 1. If I pull out a negative 1, I get a positive 11x minus 6. And the problem is, if grouping is going to work, these two things in the parentheses have to be the exact same thing. They're not. So that means that grouping doesn't work. I can't use grouping. So it may look like on the surface that this thing doesn't factor. Well, it doesn't factor with the grouping technique. That doesn't mean it doesn't factor at all. So to be able to solve this equation, what we have to use is the factor theorem. 3 is a 0 of this thing. So since 3 is a 0 of this thing, that means that if I plugged in 3 into the synthetic division and took this part right here, 2, negative 3, negative 11, and 6, and then did synthetic division, 3 times 2 is 6, add, I get a positive 3, 3 times 3 is 9, add, I get a negative 2, 3 times negative 2 is negative 6, add, I get 0. I get a quadratic. Okay, this was x cubed, x squared, x and constant, so that means this is x squared, x constant, and the remainder. I get a quadratic. Remainder 0, so I know 3 was a 0 of the polynomial. But I can figure out what makes this, the quadratic that's left, 2x squared plus 3x minus 2 equal to 0. I can either try to factor that if it'll factor, or if it won't factor, I can solve it with excuse me, I can solve it with the quadratic formula. But this one will factor. I can have a 2x here, x here, and then I need a number here and here. The outside inside gives me 3. So I'll have a 2 here, negative 1 here. Okay, so this is 2x squared. Outside's 4x, inside's negative 1, that's 3x, and then that's negative 2. So the one solution's 3, we know that. The other solutions come from setting these two pieces equal to 0. So add that 1 over, I get 2x equals 1, so x equals a half. Subtract that 2 over, I get x equals negative 2. So the solution set here is negative 2, 1 half, and 3. Alright, 3 from the very beginning, and then 1 half and negative 2 from this factor I get after I've done synthetic division. Okay. Now, also, the really important thing is if f of c equals 0, if plugging in 3 into the function gives me 0, right, then x minus c, x minus 3, is a factor of f of x. So why is that important? Right there is the factored form of this polynomial, right? We tried to factor by grouping, it wouldn't factor by grouping. So we may have thought, well, this is not a factorable polynomial. Well, there it is. If you multiply this out, you'll get this original thing that we started with. It is factorable. We could have factored it. It's just it didn't factor by grouping. The only factoring technique we knew at the time didn't work. Just because a factoring technique doesn't work doesn't mean it's not factorable. Okay? The factor theorem will get you a factor form of a polynomial. You just have to know that first zero to get the ball started. Okay? Now, what we're going to see as we go through this, there are going to be some times where the factors are, they'll have like a square root of 7 in here. I mean, it won't be pretty whole number factors like this, but it will be factorable. We'll be able to factor any polynomial. Okay, so just know that if factoring by grouping doesn't work, that does not mean at all that your polynomial couldn't be factored. It just could not be factored by grouping. Alright, we will have to factor polynomials, especially in the next section, using this factor theorem.